Hello, my name is Sinwoo Kim, and this is my 5th lab report of Physics 2211. This report will consist of the introduction, principles, experiment, computational model and code, results and discussion, and conclusion. The purpose of this lab is first to observe the motion of the bottom of a falling slinky. We will compare the observed Y position data from tracker with expected data from a computational model of our experiment on GlowScript. To summarize the results, our observed and expected position data both show that the bottom end of the slinky remains stationary. However, there are some deviations as it begins to fall. Now we will talk about some fundamental principles. First, we will talk about Newton's second law, also known as the momentum principle. It states that the acceleration of an object depends on two factors, net force and mass of the system. F net equals mass times acceleration. By manipulating this equation, we can derive two other important equations used in this lab, the velocity update and the position update formulas. These will be used to create our computational models. Lastly, there are three forces we are focusing on and how to find each of them. Gravity on the surface of the Earth is just minus mg pointing downward. The Slinky force is a tension force that counteracts the gravity, mg in the positive direction. The drag force is minus bv squared times v hat. Note that the negative times v hat means the drag force points in the direction opposite to velocity at any given point. The experiment was conducted by letting a slinky hang down due to its weight and then dropping it from rest. The system is a slinky and the surroundings are the Earth. I then tracked the position of the bottom end over time using tracker. The experiment was uploaded and calibrated to the initial conditions. The calibration stick was Derek's height, which an average man is about 1.77 meters tall. The mass of a standard slinky is 0.172 kilograms. The x-axis was placed on the ground with the origin directly under our slinky. The time starts at 0 seconds when the slinky was let go, and each time step between tracker points is 0.667 seconds. We are focusing on the time and Y data points that tracker returns. To create the computational model in GlowScript, I first had to set the initial properties of the experiment, which are the slinky's position, mass, and initial velocity, which is 0. I also defined the gravitational constant and drag coefficient, which is found using trial and error to match up our expected data as closely to our observed as possible. For the first while loop, we're looking at the time frame before the bottom of the slinky started falling in our experiment, and the forces acting on our system now are gravity and the tension force. We calculate these and sum up net force, which can be plugged into our velocity and position update formulas to predict the future motion. For the second while loop, we're looking at the time frame where the bottom of the slinky is moving, and the forces acting on our system here are gravity and drag. We calculate net force once again, plug them into the formulas, and get expected data. This is a picture of the model's trajectory. Using Excel, I've plotted the observed versus expected Y position data on the same graph so we can see how they correlate. The light blue line is my observed data from tracker. The navy blue line is my expected data from GlowScript. As you can see, they both similarly show that the bottom end of the slinky remains stationary at first, and then it begins to fall. Therefore, we can infer that the forces in each part of our model were defined somewhat correctly. During the fall, there are noticeable deviations and error between the expected and observed data. Therefore, we need to cover possible sources of error. The main source comes from manually having to track the slinky's position on tracker, which can be quite difficult considering it's an object on video being clicked on by a mouse. It's hard to tell if the mouse is clicking precisely on the bottom edge of the slinky. Also, the video quality is not the best, so sometimes there is motion blur. Another source of error would be having to determine the drag coefficient using trial and error. I tried to get the data as similar as I could, but was unable to match it exactly. My drag coefficient is likely a bit off. Lastly, in the real world, there are likely unaccounted external forces acting on our slinky that contribute to deviations in motion. So, to conclude this experiment, here are two questions pertaining to our models. Why does the bottom end of our slinky remain stationary? This is because while the slinky is stretched and exerting a tension force equal and opposite to gravity, the y direction net force cancels out to just 0. An object at rest remains at rest unless acted upon by a net force. When will the bottom end of a slinky begin to fall? It begins to fall once the top end meets the bottom end and the slinky is no longer stretched nor compressed. There is no tension force being exerted to counteract gravity. Alright, thank you for your time and have a nice day.